Hello and welcome to The Explainer. Today we're diving into one of the most compelling, almost romantic ideas in all of physics, the theory of everything. You know, the hunt for that one single master equation that could describe our entire universe. But what if that whole epic quest is actually based more on a desire for beauty than on, well, hard science? That's a quote from physicist Sabine Hossenfelder, and it really sets the stage for what we're about to do. We are going to question a really deeply held assumption in science. So get ready, because you might end up seeing the universe just a little bit differently. Let's get into it. So here's our game plan. We'll start with the ultimate quest for a final theory, then look at the four forces it's supposed to explain. We'll explore the dream of unifying them, and then we'll hit the brakes and look at a powerful critique of that dream. And we'll finish up with a new, better question that we should all be asking.
All right, so physics' ultimate quest. For decades, this has been the holy grail, right? The search for one elegant, all-encompassing theory that just explains everything. So what is a theory of everything, or a TOE as they called it? The goal is to weave together all the fundamental forces of nature into one single, coherent picture. It's this beautiful idea that underneath all the chaos and complexity of the cosmos, there's just one simple underlying principle. Now, to even begin to understand that quest, we've got to meet the main characters. What are these fundamental forces that this theory would have to somehow bring together?
Turns out, physics says there are just four fundamental forces. You've got electromagnetism, the strong and weak nuclear forces, and gravity. That's it. Any other force you can possibly think of, like the force your muscles use to lift something, or even the weirdly strong pull that sends you down a Wikipedia rabbit hole, it's all just a side effect of these four working in concert.
Okay, but here's where the trouble really starts. Three of those forces, the electromagnetic, strong and weak, they all kind of hang out together. They follow the bizarre rules of quantum mechanics, and they're described by what's called the Standard Model. But gravity? Gravity's the loner. It's the outlier. It's described by Einstein's general relativity, which is a totally separate classical theory that has nothing to do with quantum mechanics.
And you might be thinking, okay, so what? Both theories work amazingly well on their own turf. So what is the actual problem here? Why can't we just let them be? Well, the problem is that their math is just fundamentally at odds. It's like they're written in two different languages that just don't translate. The rules of the quantum world and the rules of gravity clash. We know tiny quantum particles have gravity, but when we try to describe how, our theories just fall apart. That gap, that mathematical mess, is exactly why physicists are searching for a theory of quantum gravity. And this, of course, leads us to the grand dream of unification. The thinking is, hey, if we have to fix this one mathematical problem, maybe we can just go all the way and unite everything while we're at it.
So physicists came up with a kind of two-step roadmap. Step one, create what's called a grand unified theory, or a GUT. This would merge the three quantum forces into one. Then, step two, the final boss, merge that GUT with a working theory of quantum gravity. And boom! You'd have your theory of everything.
Now, the reason we don't see this perfect unity, the theory goes, is that it only existed at the insane energies right after the Big Bang. As the universe cooled down, that perfect symmetry broke. Kind of like how steam, which is just one thing, condenses and breaks into countless separate water droplets. We're left with the four distinct forces we see today. Okay, that all sounds pretty logical, doesn't it? But now we're getting to the real core of the argument. What if the motivation behind this whole grand quest isn't totally scientific? And this, right here, is the absolute key question. We've established that we need a theory of quantum gravity to fix a real mathematical problem. We have to do that. But do we actually need to unify the other three forces? Is there any experiment, any observation at all that's telling us they have to be connected? According to physicists like Hossenfelder, the answer is a hard no. The Standard Model works perfectly fine with three separate forces. And that leads to a really provocative conclusion. Maybe the entire push for a theory of everything isn't driven by evidence, but by something else entirely. And if you look at the history here, the argument gets even stronger.
The search really kicked off in the 80s, and it was openly driven by this desire for beautiful, simple laws. And to their credit, scientists proposed theories you could actually go out and test. The problem? To date, every single one of those testable ideas has been proven wrong by experiments. The data just isn't playing along.
I mean, this quote really says it all, doesn't it? It's a blunt and maybe necessary reminder that science is about what is, not what we wish was true. It doesn't matter how beautiful or elegant your math is. If it doesn't match reality, it's just wrong. So where does all this leave us? Well, not hopeless, but I'd say empowered. It gives us a new, sharper way to think about these big claims in physics. And it all comes down to asking the right kind of question. The next time you see some big headline about a new theory of everything, don't get sidetracked by wondering if the math is right. Look, the people cooking these theories up are brilliant. The math is almost certainly correct on its own terms, but that is not the important question to ask. Here's what you should ask instead. 1. What actual problem in our current theories does this new idea fix? Is it solving something real, like that quantum gravity mess? And 2, maybe the most important question of all. What's the evidence? Why should we believe that this specific, beautiful piece of math has anything at all to do with the real world?
It really does all come down to this. Aesthetics, beauty, they can be great guides, they can inspire scientists, but they can never, ever replace cold, hard evidence. Because it's pretty is a perfectly fine reason to hang a painting on your wall, but it's not a scientific reason to believe a theory is true.
And so that leaves us with one last, pretty provocative thought to chew on. Could this decades-long obsession with finding one beautiful, unified theory actually be holding physics back? By chasing an aesthetic ideal instead of just focusing on the known problems, could we be missing other, maybe messier, but more productive ways forward? It's a really good question to think about.